Hi, I'm Haaroon Yousaf, and with George Kappos, we will be discussing and presenting our work on an empirical analysis of privacy in the Lightning Network. This is done in collaboration with many of our peers. So we all know that Bitcoin is not private, and there have been many scientific papers of tracing coins between users and linking services together. There's also been extensive work in clustering algorithms, which look at finding out who owns what address. All of this has also resulted in new privacy-focused coins, which seemingly solve these problems, but these are also fraught with privacy issues and are not as private as they seem. In addition, we know that Bitcoin is not currently scalable and has scaling issues, which makes it nowhere near the high throughput of systems like Visa. This has led to new off-chain scalable payment systems, which seem to address the privacy and scalability issues, one of which is called the Lightning Network. So there are four main privacy properties in the network that it aims to achieve. Firstly, channel secrecy, which ensures that only the users involved in private channels are aware of its existence, and even for public channels, those who open the channel should remain secret, as well as those who will receive the funds. This third-party balance secrecy, which states that although the total capacity of a public channel is known, the exact individual balances of participants are only known to them. We have off-path payment privacy, which ensures that any Lightning node not participating in a particular payment should not know anything about it. And lastly, on-path relationship anonymity, which aims to make it impossible for intermediate nodes that are involved in forwarding payments to identify the other participating nodes, other than the predecessor and successor. Our contributions are as follows. For channel secrecy, we created property tracing heuristics. Here we identified more than 27,000 private channels, and in most cases, at least one of the participants. In addition, for public channels, we were able to identify who opened and who closed the channels. For third-party balance secrecy, we created balance inference attacks. Here we designed and implemented a new attack which identifies hidden balances without relying on the client's error messages. On payment privacy, we created a payment disk detection attack. Here we designed a novel attack that allows a well-resourced adversary to infer the majority of the network's payments. And finally, for on-path relationship anonymity, we created a path discovery attack. Here, an intermediate hop can infer the payments sender with a very high probability. So we should first talk about background about the Lightning Network. So let's say we have two people, Alice and Bob, and they want to send multiple transactions to each other. They have two options. Either one, they send multiple Bitcoin transactions, which cost lots of time and money, or two, they could also create a Lightning channel. Here they create a funding transaction with a 2 of 2 multisig where one of them creates funds and puts them in an escrow. This is then announced to the blockchain as an opening transaction. Now, these two people have a channel. They can now send coins back and forth to each other. So, for example, the first instance, they have 1 and 0. They then create a series of off-chain commitment transactions, which are signed by each other, which state that Alice has sent Bob 0.2 Bitcoins, and then Bob confirms this. They can create many commitment transactions between each other. And once they're finished, now we have Alice has 0.2, Bob has 0.8. They can decide to send this to the blockchain and close their channel. Then create a closing transaction, which is then broadcasted to the chain. The blockchain here acts as a verifier, and if there are any problems, or for example, if Alice or Bob try to cheat one another, they can then send the blockchain a proof to say that this is not what had happened. So let's start with the differences between public and private channels. In public channels, everyone knows its existence, as it sits on the whole network. The capacity of the channel is known. Anyone can use it for routing, and also when it's closed, the funds are kept anonymous, meaning it's not known who takes the funds. In a private channel, only the participants know, and these channels are not announced to the wider network. Because they are not announced, only the participants know the balance, and the capacity is hidden. However, if they so wish, they can tell their friends and other participants about the channel, who are then able to use it. And lastly, just like public channels, when it is closed, whoever takes the funds are kept anonymous.
So now that we have seen how two users can share a channel, let's take a look at the broader view of the network. Let's assume that Lightning consists of these nodes we have over here that share the following public channels. And we have private channels as well. The main thing to notice here is that in order for two people to send payments to each other, they don't need to hold the channel between them. Instead, they can use the so-called HTLCs or hash time lock contracts. In the scenario where Charlie wants to get paid by Bob, as we can see, they do not share a channel between them. What happens is that Charlie would generate a secret X, will compute the hash of the X, and will send a message we call the invoice to Bob that includes this hash of X, as well as other information like the amount Charlie wants to receive to Bob. Then Bob will have to find a path between him and Charlie that can facilitate this payment. Basically, this means that he has to find those nodes between Bob and Charlie that have enough outgoing balances in order to facilitate the payment. The HTLCs provide two very important features. First of all, two nodes can communicate with each other and send payments to each other without having to share a channel, but also it ensures that intermediate hops that are involved in a payment, they cannot cheat in the sense that they cannot receive a payment without forwarding one as well. Before diving into the details of the privacy properties and how we tackle them, we're going to try to motivate their importance by comparing the tracing of funds in Bitcoin and Lightning and what are the main differences. So we're going to use a scenario where Bob gets hacked by Eve and Eve requests ransomware in the form of Bitcoin. Then Bob will create a Bitcoin transaction that sends money to Eve. This transaction is transparent and everyone can see it in the blockchain. Let's assume that Eve wants to exchange those coins for money. So for that purpose, she's going to use an exchange. But since both of these transactions that we see here are transparent, and research has shown that it's very easy to trace funds in Bitcoin in the Bitcoin network, what the exchange can do is that they can implement the anti-money laundering policy and inform a law enforcement agency that they have received funds that have an illicit origin. Let's try to see what Eve would do in the case that she wanted to launder her funds using Lightning. In this case over here, she says she shares a private channel with Charlie. So the question here that we're going to tackle is who's interacting with Eve? Does Bob, who shared a public channel with Eve, know anything about her private channels? A second question is whether Eve, who is not sharing a channel with either Alice or Bob, can infer the balances that they have between them, which, as we will see, has a very important consequence. So what are Alice and Bob's balance according to Eve? The other question is, Eve, who is not involved in a payment between Alice and Bob, can she infer the fact that they're actually communicating with each other and they're sending payments? The last question we're going to tackle is whether Bob, who is an intermediate hop between Eve and Charlie, can infer who the sender of the payment is. As we see over here, neither the predecessor or the successor of Bob is Eve, so in theory, he shouldn't be able to infer who the sender of the payment is.
So first start with private channel secrecy, and we'll first start with what we know. So we know that on-chain, private channels are indistinguishable from public channels. But we also have a list of all public channels, which we can collect by scraping the node. We also know the time period of when the Lightning Network was formed. And lastly, using the list of public channels and creating our own private channels, we can derive features which are used by channels that distinguish them from others. The question now is, using all these, can we find out other channels on the network? We now explore the property heuristic. This uses features from transactions to identify the upper bound of private channels. And we first find transactions which are between January the 12th and September 7th. These are our limits. We then filter these with the channel opening features. For example, firstly, we found that 99% of channels had at most 2 outputs. So far, that over 99% of channels had a single pay-to-witness script hash as an output, and that 99% of these channels, the output had received less than 0.16 Bitcoins. There are other features, however, they're not all iterated. Combining all these together, we're able to determine and find approximately 260,000 potential transactions, which are features of channels that have been opened. We then filter these with the features for closing channels, which can be found in the paper, leaving about approximately 77,000 potential open and closed channels.
So the main purpose of the property heuristic was to identify the upper bound of the existence of private channels in the network. Now we'll see how we're able to find the subset of those transactions for which we had higher confidence of. The main idea of the tracing heuristic is that wallets that are used to handle public channels are the same that are used to handle private channels as well. So our methodology in a nutshell is the following. We identified on-chain all openings and closings of public channels. We clustered together openings and closes on the base of a common Bitcoin wallet that operated those. And we identified the lightning entity of every cluster. Let's see it in a bit more detail. So in this case over here, we have two Bitcoin transactions that we represent with the boxes. The input edges are the input coins and the output are the output coins. So in this case over here, the Lightning, by looking into the Lightning network, we get the following information. Well, for channel 1, either Alice or Bob opened the channel because these are the participants. Similarly, for channel 2, we have Alice or Charlie as the candidate openers. According to the channel secrecy property, as we said, we should not be able to distinguish which exactly entity opened both of those. But using the blockchain information we have, because as we said, it is possible to find on chain the openings and closings of public channels, we get the following information. The coin address 1 was the one that was used in order to open C1. But the coin CH1 was used to open the channel C2. But a very simple blockchain analysis will show us that the coin CH1 is the actual change that was created by the blockchain transaction TX1. So there is extremely high probability that C1 and C2 were actually opened by the same Bitcoin wallet. By given the intersection between the two pairs, we actually know now that Alice was the one who opened those channels. And this particular feature was very persistent in the entire blockchain in regard to Lightning transaction. The users used to create a very long pill chains, as we call them, of continuously opening channels. In this case over here, we know that Alice opened channels C1, C2, and C4 within the same pill chain. But within this pill chain, we also identified another transaction that satisfied all the features that were present in the property heuristic. So now we have an identification of a private channel with very high probability. And not only that, but we can also infer one of the private channels participants, which is Alice. Now let's see how we're going to identify the second party of this private channel. We're going to look into the closing transaction. In this case over here, the coin address 3 was the output of the closing of C3. But this particular coin was used to create C5 and C6, and which, given our earlier methodology, we can infer it was Dave. So now that we know that the second party of our private channel is Dave. We did this analysis for all the public channels we had, and we identified more than 27,000 private channels with very high confidence. Moreover, in more than 79% of the cases, we were able to identify one participant, and in 7.5% of the cases, we were able to identify both of them. In 13% of the cases, we're not able to identify either participants of the private channel. We did this analysis, of course, for the public channels as well, and we figured out that in 89% of the cases, we were actually able to break the channel secrecy in the sense we were able to identify which particular node opened the public channel. In more than 77% of the cases, we were also able to identify who received the outputs of the closing transaction.
So as previously explained, channel balances are only known by the channel participants. This ensures that they maintain their privacy while transacting with one another and maintain the privacy of forwarded payments. However, what about the case when an active attacker wants to dynamize the channel? In previous research, we've seen an Oracle attack. Here, an attacker creates a channel between Alice and Bob. They then route a payment here with a fake pre-image between Alice and Bob. Now, either once received, depending on the status of the message, would reply. If the message was successful, the attacker would receive a message claiming that Bob cannot claim the pre-image. If the attacker was unsuccessful, then attacker would receive a message claiming that the Alice was unable to forward the payment. Now, this here is heavily reliant on error messages, which can be patched. So here we now describe a generic balance inference attack, which does not rely on the contents of the underlying message. Here, for example, the attacker selects a target and opens up 2 channels, one on each side. The attacker communicates with each other as they're expecting a message to be received. Just as follows, the attacker now routes a payment of an amount with a fake pre-image hash through Alice and Bob, which is expected to be received by the attacker on the other side. Now, if the node received the image and is able to determine what the pre-image was, then they are aware that the sufficient balance is forwarded. However, if the attacker does not receive the pre-image in time, then clearly something had gone wrong, and they can just simply repeat this attack with binary search. Here, they are not reliant on an error call, but rather whether a message was received that contained the hash. We performed this attack on every node in the testnet with 2 lightning nodes and fund all the channels. We were able to attack 103 nodes, which consists of 3% of the network, and 11% of all channels, which was 1,017. However, not all channels were active or responded to connection requests or channel openings. We found that 65% of the channels were one-sided, meaning that the balance of the attacked party was 70% or more of the total capacity. Now, this attack is not very cheap. On the testnet, the coins are useless. However, we estimate that if you were to do this on the main network, you would have to purchase incoming liquidity. You would also need approximately 1 Bitcoin's worth in cost to make channels, over 109 Bitcoin's worth to hold these balances in escrow and able to attack the entire network. So here we know that the sender, receiver, and the amount. But can we extend the attack just from before to a payment inference? So if the balance of a path changes by a small amount, it's likely that a payment was a process between the edges. So what we could do is run a balance inference attack on all edges at a certain point in time, and do it again at another point in time in order to receive 2 graph snapshots. We could then look at the differences between these 2 graphs in order to determine if you could find the edge value between the payments that were sent. So in the example here, we have 2 snapshots run at 2 different points in time. And the idea here is, can we compare the 2 obtained snapshots to infer information about the payments and the paths that took place. So we perform a simulation where we choose a random set of senders and receivers with small payment amounts to simulate a worst case scenario. For the snapshot, we use a time of 30 seconds and we're able to recall 66%. However, this attack does not need to target the entire network. This attack can target a small subset of nodes. And secondly, in reality, the payment amounts vary significantly and therefore would only increase the accuracy of our algorithm.
Now we'll describe how we build a landing network simulator in order to facilitate a last observation regarding the on-path discovery. Our goal in our simulator was to create 2 distinct simulations. We call them length long and length short. In the first case, we try to maximize the path lengths and at the same time minimize the probability of a payment failing due to insufficient balances. In our second simulation, we try to achieve the exact opposite. So a question could be here, why did we not try to find the most realistic simulation instead of having an upper and lower bound approach? Well, the reason was that we needed significant resources to achieve a very realistic simulation. And most importantly, we had to make assumptions regarding the network that are unknown. So instead, we followed the upper and lower bound approach. So to build a simulation, the first type of parameters we used are the node and network parameters, which most of this information is known in the entire network. So information regarding the network topology, the capacity of the channels, and the fees that the nodes charge. We collected this information by having an LND client running and scraping every 1 hour. We're also able to estimate the geolocation of the nodes based on their advertised IPv4 and IPv6 addresses. Lastly, we simulated the delays between the nodes by using the global IP latency from Verizon. The second type of parameter was much trickier to simulate. The first type of our parameter is the payments endpoints, which basically define that we have a payment. We need to define who is the sender and who is the receiver of this payment. For this, we use two distributions, uniform and weighted. The uniform distribution says that when you have a payment, you choose the sender and the receiver completely randomly. The weighted one says that you do choose randomly, but you take into account the node's connectivity. So basically, the more channels you're going to have, the higher the probability that you're going to be selected as an endpoint of the payment. The second type is the payment values, which needs to determine what is the amount of the actual payment that's going to be forwarded. We define two distributions here, cheap and expensive. Cheap says that the payment value is the smallest possible value that the sender can send. Expensive means that the value that you're going to choose is the most expensive given your current balances. So let's see how these parameters fit into our simulations. As I mentioned earlier, length long wants to achieve the longest possible path lengths and at the same time minimize the probability of having your payment failing due to insufficient balances. So for this point, for this simulation, we used uniform for endpoints because uniform meant that our routers, which are basically the nodes that are extremely well connected in the network and have many, many channels, uniform meant that we're going to have less of these routers used. So the paths would be actually longer because these routers have so many channels that they make paths very small if they're chosen as the endpoints. Similarly, we used cheap values because we wanted to minimize the probability of getting insufficient balances. And accordingly, we used weighted for payments endpoints for length short and expensive for payment values. When we fed this data into our simulations, we figured that in the scenario where we wanted to maximize the path lengths, even in this case, almost 15% of the payments had still only one hop. When we tried to make them as short as possible, more than 56% of them had one hop between the sender and the receiver. So now that we described as two simulations, let's see how they fit in our observation regarding the on-path relationship anonymity. So this privacy property ensures that an honest but curious intermediate node cannot guess the sender or the recipient with more than negligible probability. But let's define a game here when the honest but curious intermediate node wants to find the sender. His strategy is very, very simple. He will always guess that the predecessor node is actually the sender. He needs to keep his channel balanced. And the question here is, what is the probability of this adversary being right? Let's assume the scenario over here, where there's only one hop between the sender and the receiver. And the question here, in this situation, when is he right? Well, he's always right, because when there's only one hop between the sender and the receiver, then the intermediate node's predecessor will indeed be the sender every single time. But what about when you have two intermediate nodes? How often is the adversary right? Well, this actually depends. If you thought about 50%, then you're close, but it's not the case every single time. And this can be extended to multiple hops between up to 20, which is the maximum for the Lightning Network. So putting it all together, the probability of our adversary being right is the addition of all these intermediate probabilities. So the first part of this probability is directly extractable by the measurement we had earlier, because this probability says what's the chance of a path being of length L. And this probability, as we said, varies from 15 to 56.65%. The second part says what is the probability of me being the first hop among all possible hops. Well, the lower bound of this probability is that the adversary is always wrong when there is a chance that he is wrong. Another calculatable approach is when all nodes in a path form a clique. Well, in this situation, the probability of me as an intermediate node being in a particular hop is 1 divided by the total number of hops, because it's equally probable to be in any hop. By feeding these numbers into our probability, we saw that in the worst case scenario, the intermediate node had almost 15% probability of being right. But in the best case scenario, where the paths are short and the failures happen frequently, and there was a clique forming the particular path, this probability skyrocketed to 83%. So as we said, since we wanted to avoid a realistic case approach, because this would require to make assumptions about the network, we were able to actually find the lower and upper bound of the probability of breaking this privacy property. And this range is from 15 to 83%. So now that we have described the four most important privacy properties of Lightning, we hope that we gave you, we showed you how we try to tackle each and every one of them. If you have any questions, please feel free to ask.